This assignment is about I/O, so you need to do a lot of printfs and scanfs. It's about creating a program that converts tabular data between two formats. It can convert a TXT to CSV or a CSV to TXT. So that means what? That means TXT format for tabular data is tab delimited. What does tab delimited means? It means that you have one row in each line, and in each row, basically, or in each line, basically, the cells are separated by tab. That's called tab delimited tabular data, or TXT. CSV is very similar to TXT in the sense that every row is in a separate line, so each line represents one row. The difference between CSV and TXT is that in CSV, which stands for comma separated values, the values of different cells in a row are separated by comma, not TXT. Also, for the sake of simplicity, let's assume the following. Let's assume that when you have a TXT file, there is no tab within a given cell, right? So whenever you see a tab, that means this is basically the border between two adjacent cells, right? That means when you have a TXT, there is no tab within each cell. So the tab is only used for separating two adjacent cells. And similar assumption for CSV. Let's assume that when you have a CSV format, there is no comma within each cell's content. That means what? That means whenever you see comma, without any exceptions, that comma separates two adjacent cells, right? So you cannot store a string containing comma within a cell in a CSV file, and you cannot store a string containing tab within a cell in a TXT format. These are restricting assumptions, but this is a good assumption for this assignment to be a little bit simpler. I don't want to complicate things because, what's the point of doing that as long as you understand how to do the I/O? I mean, these extra complications is not going to help anyone. So we're going to use these simplifications to make things easier. Now, how does this program work? First of all, whenever you create a makefile for this program, make sure to call the executable name convert. Now, in this program, which is called convert, you're allowed to use some command line arguments. The user who runs the program may pass different command line arguments. What are those? Let me start from the first one, -i format. -i is a flag followed by a three-letter string, which is specifying the format of input, either CSV or TXT. So after -i, you expect either CSV or TXT. If there is no -i, then the default input format is TXT, right? So you're allowed to run the program without any -i flags because there's a default value for it, which is TXT. Then we have -o followed by the format, which specifies the output format, which is either, again, either CSV or TXT, but the default output is CSV. I made a mistake here. I said default input, I meant default output. So I'll fix that. Anyways, -e is another flag, which basically makes your program convert the values of cells containing double values to their equivalent normalized scientific notation with 3 digits of precision after the decimal point. So that conversion looks a little bit weird or scary, I should say, but don't worry about it because you don't need to do this conversion yourself. If you use printf, which you need to use printf for printing the results on the output, in order to convert any double to a normalized scientific notation with 3 digits of precision, all you need to do is to use a placeholder %.3e. So that placeholder inside the printf function is going to take care of this operation for you and is going to generate a normalized scientific notation with 3 digits of precision. I'm going to briefly show you what I mean. Then later, after I get into the code, then I will have -x. That option -x makes your program to convert the values of cells containing integer values to their equivalent hexadecimal values. For example, if you're converting 12 using -x, 12 in decimal is equivalent to letter C in hexadecimal. Or for example, 10 is A, or F is 50, or 15 is F, or 16 is 10, so on and so forth. Again, to make an integer hexadecimal, you don't need to do the conversion yourself. All you need to use is the %x placeholder that exists and works with printf. So you don't need to do the complicated things yourself. You need to use the options and placeholders that printf provides, right? So it's not a big deal. Yeah. You have 7 days from today to do it, but you don't really need 7 days. However, I would strongly urge you to start right now, but you don't have a big task to do because most of it will be done by printf. All right. Then you have you have -s, which is another flag, which makes the program to truncate the values of cells containing non-numerical strings. When I say non-numerical strings, I mean if your cell is neither integer nor double, then the %s, or I'm sorry, the -s can make your program truncate those values to prefixes of length 5. For example, let's say a cell contains the word hello, the string hello world, right? So your cell contains hello world, hello space world. With the option -s, your program will truncate everything after hello because hello is 5 character long, and everything after that should be dropped because of the -s. But if there's no -s, the hello world itself, the whole thing will be transferred to the output. So the input and output would be the same. But if you use -s, we only use the first 5 characters of every cell that is non-numerical. If it's numerical, then -s has no impact on it, right? Basically, -e was only affecting double values. -x only affects integer values, and -s affects non-integer, non-double values. So if a value is neither, if a cell value is neither integer nor double, -s will affect on it. Otherwise, it doesn't have any impact on those. And then finally, -c makes the program to remove leading and trailing white spaces from each cell of input data. This is the only part that printf is not going to help you. I will help you instead. I'll show you, and I'll post the code that basically removes the leading and trailing spaces for you. It's not a big deal. I'll show you how it looks like. All right, so the IC basically clears everything, right? Clears the content of a cell and removes the leading and trailing spaces. I call the function strip. I'll show you later because it removes the spaces from beginning and end. That's a very common, operation when you're doing text preprocessing in different programming languages. There are libraries that have this operation. Normally the function or method are called strip because it just removes the spaces from beginning and end. All right. Now the test cases. I will definitely post the autograder for this one tonight, but let me just give you some examples first, and then I'll post the autograder. The autograder has some other examples as well, or has like different examples. You can use that to test your code, but let's first go over some basic examples, and then you will find out how all of these flags and options will help the user to customize the process of converting a CSV file to a TXT file, or vice versa, converting a TXT to CSV. Both directions should work, CSV to TXT and TXT to CSV. Here is the input stream. Let's say the user enters these through keyboard. 12, this is the tab sign. So 12 tab, negative 12.3 tab, a few spaces, hello world, a bunch of other spaces, new line, a few spaces, sentence, a few spaces. Then I have tab, 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 new line, tab 23 point, tab negative 23, and then control D, which is a shortcut for pressing end of file to close the input stream. When this is entered, then your program should convert the input to output and print the output. Or it can generate the output after every line. That's okay too. But control D basically ends the whole input stream, and then therefore your program should immediately print the output and then end the whole program, because if there's no other input, your program should not continue running. Okay, so given this input stream, I'm going to make some assumptions about command line arguments, and for each command line argument, I'm going to show you the expected output, right? But in each of those cases, I'm going to assume the input is the same. The input is these 3 lines that you see here, nothing else, right? So let's first assume that the command line arguments are nothing. Just say the user enters convert, right? And when I say convert, let me make it a little bit clearer. I mean ./convert, right? I don't mean the convert is the name of the executable. So in order to run it, you need to start from ./. So similar to other assignments, always start your executable name with ./ so that the operating system knows you want to run it. But there's nothing else. That's the name of the executable. There's no other command line arguments. There's no -i, no -o, no -e, no -x, no -s, no -c, nothing. And the input was a TXT, right? Was a tab delimited. The input looks like this. The input looks like this. So how should the output look like? Well, all you need to do is, because you want to convert the default input format, which is TXT to CSV, replace all the tabs with commas. So in the first line, when you have 2 tabs or 3, you have 2 tabs, with one between 12 and negative 12.3, and one between the 12.3 and hello world. Both of them should be replaced by commas. So all you need to do is replace tab by comma. That becomes your converted row. That's the first row. The second row for in input was a single cell containing the word sentence with a bunch of spaces before and after it. And then there were 3 extra tabs showing 3 empty cells that comes after sentence. So those 3 empty cells should be replaced by 3 commas, right? So the tabs will become commas. And then we do have the third line as well. The third line is tab 23 point, tab -23, and then end of file. So instead of tab, we just put comma, and that's going to be how the last line look like. Any questions? All right. So now let's make it complicated. Let's say you have -e, -x, -s, and -c. So you have all of those 4 flags that clears each cell from the spaces, and use scientific notation for doubles, use hexadecimal for integers, and use the 5-letter prefix for non-numerical values. How does that affect the conversion process? So instead of 12, you now should put C, because 12 is an integer, right? So the int hexadecimal representation of 12 is C. Again, printf has a %x placeholder that does it. -12.3 in scientific notation will become this. -1.230 is +01. And the hello world with 5-letter of prefix would be only hello. The next line, because I have a -c as well, I have to remove the spaces before and after sentence. So I don't have any leading or trailing spaces. And then because of -s, I have to shorten my sentence and convert it to SENTE, and that's it. Only the first 5 characters. But remember, the -c will clear the spaces first, and then -s will drop any character after the 5th one. So when you have both -c and -s, first apply -c to clear everything, and then after removing all the spaces, then you use -s to truncate all but the first 5 characters, or truncate everything after the 5th character of the string. And then finally, we have in the last line, we have an empty cell followed by 23. 23 again is a double value because of this dot. You see this dot? That makes the number a double. If it was integer, then you have to treat it like a hexadecimal, and 23 in hexadecimal would be 17. But because of the dot, it's a double value. So when you convert it, you have to convert it to a normalized scientific notation, which is 2.300 E plus 01. Why do we have 2 zeros here? Because the question said in normalized scientific notation, don't forget to add 3 digits of precision. So this is the number with 3 digits of precision. And then you have -23. That's your -23 in hexadecimal. The reason that we have these Fs is because when a negative number is represented in the computer hardware, you have 32 bits of representation for a negative number that is in 2's complement, and the number in 2's complement starts with a bunch of 1s if it's negative. In this case, -23 is a very small negative number, so it should start with a lot of leading 1s. Every F represents 4 1s. So because we have 6 Fs here, that means you have like 24 different 1s. And then E is 1110. So basically you have 27 1s leading the number, and then 9 is 1001. So you don't need to be worried about this part. This is going to be done by the printf itself. I just wanted to tell you this weird looking number is the hexadecimal representation of -23, and everything is fine in this case. All right, any question about the second example? I hope you hear me because I said a lot of things and no one
Yeah,
has
we hear you.
questions. Good,
We got you.
good. So that means my explanation was clear. So great. Next, we have convert -I txt -OCSV. These 4 flags are gonna do nothing because the default input format is CXT and default output format is CSV. So they have no impact because they're basically setting the in format and out format to the same default values. So the output of the third step, the third example is the same as the output of the first example. So exactly the same output is expected, and that's what you see on the output. The fourth row shows you the command and arguments that explicitly says the input is txt, output is CSV. Again, these are default values. So this fourth row basically has the same impact as the second row's command and arguments. As you see in the second one, the orders are EXSC, but in the fourth one, the order is different, but doesn't matter. The order of command and arguments doesn't change their meaning. Therefore, the fourth output is going to be the same as the second one. There's no difference. The fifth one, however, is completely different. We're going to assume the input and output formats are the same, CSV to CSV. When you're converting with the same input and output and no other flags, your program behaves like a very simple echo program. Echo program is a program that echoes the output, echoes the input to the output without any changes. So when you're converting from one extension to itself, nothing should happen. That's an echo program. It's a simple program that does nothing. So the output is basically the exact same copy of the input, right? Nothing happens. What about if you want to convert CSV to TXT? That's a tricky one. If you convert CSV to TXT and the input is more like a TXT than CSV because there are tabs, and it seems like the tabs should separate cells, right? But if the user says, although you have multiple tabs in the input, but this is a CSV format, right? So we're going to believe the user and say, okay, if this is a CSV format, so it means that every line that you write is only one cell because there's no commas, right? So if there's no comma, that means the whole line is a single cell, right? Because in CSV, cells are separated by comma in each line. So because there's no line, each line is treated like a single cell. And because the output is TXT, we're going to echo that on the output without any change, right? We don't change anything, we just output it. And that's the story of the last one. Any questions? All right, and then for the submissions, make sure to have a zip file that contains all your C files and H files if you have any H files, and also the make file as well. That should be included. And then the word convert is the executable of your program. So make sure within your make file, set the executable name to convert so that you can get the credit for this assignment. Before I show you the starter code, which I have prepared for you, I wanted to know if you have any questions. No? Okay. So let's see the code. So here is my code. I have created some macros and enumerators and functions that will help you manage this program easier. You're free not to use it and use your own code, but I just, while I'm showing you the starter code, I'm also want to teach you a few things about C programming, like how enumerators can make your life easier for, let's say, command line argument handling. Okay, and how to use bitwise operations and enumerators to make the options of a program stored in a single integer instead of having one flag, one integer per flag or one integer per option. We have only one integer for all the flags. Remember the assignment 2 where we defined the find program? If you remember, I had in my starter code, I have an except flag. It was an integer except. It was another integer for number. It was another integer for sort, another integer for reverse, another integer for every single other flag, right? And this is a waste of a space because a single integer is a very, versatile data structure because it's going to give us 32 bits, and each bit is can basically store a Boolean because it can get either a 0 or 1, so it can get a binary value in it. So what I can do is I can store every single flag or option of my code in 1 bit, and therefore an integer, which is a sequence of 32 bits, can be treated like a Boolean array of size 32. So why should I define multiple integers for the multiple flags? I only use one integer per flag. I'm sorry, I use only one integer for all the flags and use bitwise operations to handle that. Let me show you how it works. So the flags that I have are -C, -X, -E, and -S. I have created one line of constant in my enumerator. What is enumerator? Enumerator is something like a structure or a class in a Java programming language, for example. But it only stores constant values. It doesn't store any other values. So you're used to see structures that store, let's say, a char star or an integer or a double, different data types. But an enumerator only store constant values or constant, I should say, unsigned integers. And basically, defining an enumerator is like declaring a bunch of constants, right? It's like in Java, say, let me have a public static final int called none equal to 0, a public static final int clear equal to 1, a public static final int hex equal to 2, 1 for scientific equal to 4, and 1 for truncate equal to 8. Basically, I define 5 different constants. However, I don't define any 5 constants. I will define my constants in a way that they are powers of 2 for a certain reason. The reason is I'm going to take advantage of different bits of an integer to store all flags in one single integer. So here is the idea. Let me use my annotation tool to tell you what I mean. Let's say you create an enumerator like this and call it flags, right? Let's instantiate a variable from this flags, right? When you instantiate a variable from an enumerator, you are given an unsigned integer. What is an unsigned integer? It's a 32-bit integer. What do you have in a 32-bit integer? You have basically 32 bits, right? I don't want to write down all of them, but I'm just going to tell you like this is what you have. The rightmost bit is at index 0, then you have index 1, index 2, index 3, index 4, index 5, and then index 31. So you have 31 bits. You know, like how to convert a binary to an integer. You know that in unsigned notation, the rightmost bit's weight is 1, or basically 2 to the power of 0. This one's, the second one's weight is 2, which is 2 to the power of 1. The next one is going to be 4, which is 2 squared. Next one is 2 cubed, or 8. This is 2 to the 4. This is 2 to the 5, and so on and so forth, right? Let me use a different color now. Now, let's say I have defined a constant called clear, right? And I set it equal to 1. I can say within my enumerator, this bit with weight equal to 1, that's going to be my clear bit. What does that mean? If this bit is 1, I have a dash, I have a dash C flag. If this bit is 0, I have no dash C flag, right? The next bit is reserved for my hex flag. If this bit is 1, that means I have a hex or dash X flag. If this bit is 0, I have no hex flag. And as you see, the value is set to 2. 1 shift to the left by 1 is 2. Shifting to the left by a number of bits is going to create powers of 2. Then I have scientific value, which is set to 2 squared, which is 4. That's going to basically be represented by this bit, the third bit from right. So the third rightmost bit. If that bit is 1, I have a scientific or dash E notation, dash E flag. If it's 0, I don't have dash E flag. And then truncated or dash S is given to the program if and only if the fourth rightmost bit or this bit is set to 1. So this is my dash S. This is my dash E. This is my dash X. And the rightmost bit is dash C. Now, imagine you have many more flags. Let's say you have like 20 more flags. That's totally fine. All you need to do is to elongate this definition of the enumerator and add more stuff, more constants. And basically for everyone, you add the next power of 2. So 1 shift to the left 4 times, one shift to the left 5 times, 6 times, 7 times, gives you other booleans for other flags. I'll show you how to use these flags. Any question about this enumerator? Okay. Go ahead, Christian.
No, I'm good, thanks.
No, good. All right. So let's go forward and see how to manage the flags and use it. How to manage the program's flags and use this flag to store them. Before I show you that, let me also show you this very weird looking macro. This is a macro. The macros are defined using a numbers define. And then they're kind of similar to functions, but they're a little bit different. The compiler is not going to take care of them. Before compiler, a module similar to compiler kicks in. It's not as smart as compiler. We call it the preprocessor, and it's going to take care of macros. What does macro mean? Basically, whenever in your code you say an error keyword followed by a parentheses containing two values, one M, one C, the preprocessor will replace that code or that expression with this do while loop. This do while zero basically is a replacement for error of M and C. So this is called the definition of this macro. This is the macro name, and then the macro has two parameters, and they are untyped. There's no type for them because compiler doesn't take care of them. The entity taking care of them is called preprocessor. What does this macro do? It will use this to print a message on the output. fprintf with stderr and this is basically equivalent to saying, let's print out this message on the output. So it's printed on the console. Why don't we use a simple printf and then pass the format and then pass the message? Why do we use fprintf and then why we write stderr here? There's a small difference between these two. They both print the result on the console. The only difference is when you use fprintf and stderr, you're writing into a standard error stream, which can never get redirected from console. It always gets printed on the console. I'll show you an example of what redirection means when I'm going to run this. So don't worry about the difference. Imagine this is just like a normal printf. After it prints this message, that's an error message. That's only used when you have a fatal error. Fatal error means right after the error message, you have to exit the program. I will call the exit. Exit is a system call in the Unix operating system that will terminate the program as soon as possible and passes an error code, in this case C, to basically let the operating system know that I have failed to run this program because this happened. What happened? It passes an integer, and that integer basically is an error code. The program creator has to document the error codes, different error codes and their meaning in the documentation of the program so that everyone who's using the program knows what each error code means. But this is an error code. Right? C cannot be zero because zero is not an error code. Error codes that start from non-zero values like 1, 2, 3, 4. That's how the error codes are. Okay, this is the macro that I will urge you to use it for, not for this assignment, for the future assignments as well. This is used for any fatal error that you want to catch. And then the reason I put this in between a do while zero is because I wanted to combine these two statements into one statement so that if you place this code inside an if statement and you only have one line inside your if, and that's basically the call to this macro, you don't need a curly braces. Without curly braces, it's gonna work. So there's a deep meaning behind this do while loop. I'll show you what happens if you don't have a do while loop. Anyways, let's jump over this strip function. This strip function is only used when you want to use -c to do the clear function to remove the leading and trailing spaces. I'll come back to this later. Let me start with my main and talk about the flags, because that's a new thing we did today. We created an enumerator for it, right? So how do you instantiate a variable from this flags? This is how. You say flags flag. And by default, I'm going to set it to none because if there's no dash in the command line arguments, my flags is none, right? That means none of those bits are set, right? No C, no X, no E, and no S. The default input format is TXT. The default output format is CSV. Those are what the assumption of the program was, the assignment specification was. So I just follow those. Then I have an integer I, set it to 1. That's kind of similar to the assignment 2 starter code. Remember, there was a while loop that I traversed the argv, and for that assignment, the assumption was I have a pattern at the end, and then there are some other, flags at the beginning. But here there's no pattern, so everything is only, everything is made of only flags, either -I followed by a format, or -O followed by a format, or -X, -S, so on and so forth. So the first thing I do is I get the current argument, which is argv I, and I increment I so that, next time I check the next argument. And then what I do is get the first character of the current argument and see if it's a dash. If it's not a dash, I will just say error with fatal error, illegal command and arguments, and I pass an error code 2. This is a macro that, does this, right? If there was no do while loop, having this curly braces was necessary. But now that I have the body of error macro within a do while 0, I don't need that curly braces. So I can place the error alone within an if, and don't worry about the issue that I may get. There's no issue here. Everything is fine. So I can just remove that curly braces. If there's a dash at the beginning of the current argument, then I get to this while loop and I try to make a sense out of the current argument. I will go over like different characters of the current argument and see if they are equal to -I, -O, -C, -X, -E, or -S. If it's equal to I, that means I have a -I. So it means that I have to specify the input format. Let's compare the next argument and see if it's equal to TXT or CSV. If it's neither equal to TXT nor equal to CSV, all I need to do is call this macro again and say fatal error, and write an illegal input format error, and my error code in this case is 3. For every different error, you can generate a different error code, and this way the operating system and then finally the user knows what went wrong that it caused your program crash. But if it's either TXT or CSV, we're going to get to the else part. In the else part, I will say, is it TXT? If it's TXT, then copy TXT into the in format, and otherwise it's going to be CSV, right? So copy CSV into the in format, do an I++ argc --, because I have parsed the next argument, because the next argument after -I is going to be the format. So let's advance I and decrement argc and move forward. In the next case, if I have -O, then I will do a similar task. Again, it should be either TXT or CSV, and I will copy the TXT into out format if it's TXT, and I will copy CSV into the out format if it's CSV. And I do the same thing for I and argc. Now, if it's neither -I nor -O, it should be one of these four. If it's -C, then I need to consider the clear in my flag. Now, remember what the flag was? The flag is an enum, right? So basically, it's a constant. It's a unsigned integer. So let's say the flag is originally this, right? It's full zeros, right? 32 bits of zero. I don't want to write down all the 32 bits. Only the last 4 is what I want. So I will say let's OR this bitwise OR. This OR equal means flag equals flag or clear. Remember what clear was? Clear was 1, right? So let's OR these, right? I don't know what the 3 values are. Let's set them equal to x. X means we don't know, right? If I OR bitwise OR this value with 0, 0, 0, 1, the output would be xxx. I'm sorry. Yeah, it would be xxx 1, right? So it means that we don't care about the other bits. The bit that is corresponding to the -C flag is going to be set, right? So this line basically sets the flag bit, the rightmost bit. And then if the flag is -X, we're gonna set the second rightmost bit. And if the flag is -E, we're gonna set the third rightmost bit. And if it is -S, we're gonna set the fourth rightmost bit. And that's how you set your flag, right? So you only have one integer, but you treat your integer like a 32 Boolean that are basically placed in one array of Booleans, right? That's how powerful bitwise operations are. Okay, if none of those happens, then you need to again call that error macro that passes an error code of 5 and says you have entered an illegal option, right? All right, so that's pretty much all the error, all the command and argument handling that you need to use. And this while loop will take care of it. So I did that for you, you just use it, right? Line 76 to 85 are just there so that I can show you that my command and argument handling works. You can delete them. You don't need it for the final output, final program. I just want to place it here so you can see that I parse the command and arguments properly. So it prints into a standard output, into a standard error, a stream, which is a stream that prints the data on the console. And it's very similar to stdout, but it has some difference, which I'll show you later. And I print note converting %s to %s with options. The first %s is my in format. That's the inputs format. And then the other %s is the out format. And then the options are given here. I will, write down all the options based on what the flag is. This is where I try to retrieve data from flag. Flag was a enumerator that contains all the possible flags. So it can create any combination of the 4 flags I have: clear, hex, scientific, and truncated. And then when you want to retrieve each flag, you need to do a bitwise AND operation. This bitwise AND is basically mask and filter out all the bits except the clear bit, and ends my flag with clear. If the outcome is 0, that means the user has not entered any -C flag. If the output is non-zero, it means that the user has entered -C flag. So print -C. Do it for hex as well. Flag and hex, flag and scientific, flag and truncated. There is no need to use else here. In fact, you should not use else. All the ifs have none of the ifs have else in them. Why? Because you may have dash c, dash x, dash e, and dash s all together. So you don't need to use else. Don't use else here. Let me give you an example of why this works. Let's say, Higgs was basically the number 2. So Higgs is number 2, which in binary would be 0, 0, 1, 0. And let's say flag is, let's say x means don't care. I don't care about the bits, these bits. Let's say the flag, the hex bit is 1, and then I don't care about the clear bit. So in this case, when I AND them, hex and flag is a bitwise AND. So you need to AND 0 and x. 0 and any bits, their AND would be 0. The second 0 and the second x will give you 0. The third one is 1. 1 and 1 is going to give you 1. And then 0 and x is going to give you 0, right? Now, let's say, so the output is going to be a non-zero value. The output of these two would be non-zero. Therefore, I know that the flag has a hex bit equal to 1. Now let's consider the opposite situation. Let's say the flag has dash x, or is the x bit equal to 0. If that's the case, then the bitwise AND will give you 0, 0, 0, 0. Now, as you remember in C programming, 0 value means false, non-zero value means true. So that's why this is a great condition for the if, right? Because if it gives you 0, that's false. That means no hex. If it gives you non-zero, that means there isn't a hex. There is a hex flag set, right? So this is why this code works. Let me continue. So this is basically just to show you that my command and argument handling works. Next, I'm going to show you how to do the actual conversion. My code for conversion is quite simple. It only takes, 12 lines. And I basically use fgetS to get a whole line. The line is an array of size 1000. fgetS line 1000 and stdin. Stdin means read the data from a standard input. And then I specify the delimiter. The delimiter is either comma or tab. It depends. If the input format is CSV, it's going to be comma. If the input format is TXT, it's going to be tab, right? So that's my delimiter. Then I use strtok or strtok, which basically tokenizes the line and separates it into, or breaks it into smaller pieces. Each piece is going to be one cell. In this case, I will first pass the line, which is the whole line containing the whole row with multiple cells. And then the delimiter, which is going to be either comma or tab. And it's going to give you the very first cell, right? Then I will define an ival and dval. Ival is used whenever your cell contains an integer value. Dval is used whenever your cell contains a double value. And if none of them are used, that means you have a string, you have a non-numerical value in your cell, right? In this while loop, I will basically check whether or not I have the int value or double value or non-numerical value. The reason I have to check that is because for each value, I have to converted differently. If it was an integer value and I have a dash X option, I should convert it to hexadecimal. If I have dval or double value and I have a dash E, I have to convert it to scientific notation. If I have dash S and I have non-numerical value, I have to truncate the parts so that I can get only the first 5 letters. That's how I handle this. While cell means if there is at least one cell, or if the current cell is not empty, or if the current cell exists, do this. Use SSScanf. SSScanf is just like the normal scanf, but it gets an extra parameter. The normal scanf starts getting a format and then, some other variables that are passed by reference. SSScanf means a string scanf. So the difference between SSScanf and a scanf is in a scanf, you're scanning a standard input, but SSScanf scans the very first input parameter, which is a buffer, is a char star. So SSScanf scans a string. The string is going to come before the format, before this %d, right? So it's very simple, but it's very effective. SSScanf basically is like when you're using Java util scanner for a string, right? But the normal scanf without the extra S is like when you're using Java util scanner for system.in, right? Because in Java, if you want to scan the input, you need to scan Java system.in, but you can use a scanner to scan a string, right? Same way in C, it's a similar situation. If you use a scanf, it scans the standard input. If you use SSScanf, it scans a string. Now, what do I want to scan? I want to scan the current cell to see if it has an integer in it. All you need to do is to do this, right? Just say %d and then pass the ival by reference and see the result. SSScanf returns either 1 or 0. If it can successfully scan the integer, it returns 1. Otherwise, 0. Right? So the condition of this if would be the return value of SSScanf. If it was successful, then I have a successful parsed integer. So I will print the value, right? So in this case, use %x if dash x is given by command line arguments. This is pretty clear, but I'm just going to write it down just so for you not to forget it. So basically, you have to print the value by %x. I put here integer cell just to show you on the console so that you will see like I can recognize integer from double from a string. But you need to remove that and add proper delimiter for the output based on the out format. In the starter code, none of them are here. You need to just complete this. It takes you a few minutes to convert this to the real code. And then, for the else part, I'm scanning using LF. LF is for double. And this is going to test whether or not I have a double value in the cell. If it's not an integer, then I check the double. You cannot swap these because if you start looking for double then integer, then an integer representation is also a double representation. So that wouldn't work. So first you use %d and try scanning it with %d. If it fails, then you try %lf. And that's going to fail if it's not a double, but if it is a double, it's not going to fail, and you will print double cell. Again, here you need to use %.3e if -e is given by command line arguments. And finally, you need to print it like a string, but also you need to use the other placeholder %.5s if -s is given. All right, and you know, that's the string represent the string cell. And then at the end of this while loop, cell should be str null and delimiter. That's going to give you the next cell in the same row. And then you need to repeat this whole process again and again, because you need to, you know, scan all the cells of every row. And after you get out of the while loop, you need to continue this whole while loop to get the next row, and then, you know, do the same thing and continue doing this all the way. I have written the same code using SSScanf only without strtalk. It looks ugly, so I tried not to use it. So I deleted it, but I left it there for someone who wants to know how powerful SSScanf is. But don't look at it. Just use strtalk. Strtalk is very like easy to use. It basically means I'm gonna break my string into multiple tokens given a delimiter. First, make your program run for the cases that do not have any empty cell. So in other words, first assume that there is no empty cell in your whole table and make your program work. If you can make it work, you get full credit. But if you want, after you finish that, then try to handle the empty strings. For that, you need to change this code a little bit more. And that one has an extra 20%. So the 20% extra is given to those, 20 is too much. Let's say 15. 15% is given to those who get, those who can recognize the empty cells as well. But let's assume that your code doesn't need to handle the empty cells, right? Now, let me show you a few other things. Let me, all right, one more thing I want to do is I want to run this and I want to show you the output, and I want to show you, I want to redirect the output so I can show you the difference between printf and fprintf. That's something that I wanted to do. Let me load my Ocelot. So the code that I have written is in this directory. Let me ls it. So as you see, I have converted C. Let's compile it, gcc-o. Of course, you need to have your makefile. I'm just gonna save time and compile it without makefile. gcc-o convert.c ls. Now I have an executable convert. Let's say you try to use an illegal format, like the legal option, like -z, right? You get a fatal error and ends your program. Let's say you say -i and give a wrong format. Let's say xlsx. Again, you get an error, right? Let's say you don't make any mistake and say -i csv-o txt, and it says I'm converting CSV to txt with the options, and the options are empty because I have no other option. There's no -e, there's no -x, nothing, right? And then it waits for me to write down the input, the table, the input table. Let's say I put 1 and then 2 points and then 3 and then hello and then 4 and then world and then oh great. So that's the integer value, that's a double value, that's an integer value, that's a double value. So I managed it. Not beautifully, but after some minutes of struggling, str, chr, cell, and dot. So still that looks very very simple, so you can use this. I'm going to post this on Canvas. The last thing I want to show you is how to redirect the result into the output into a file. So let me show you what I mean. Let's do this. I'm going to run the same program. Let's say also I'm going to add -x SCE, right? Just to show you that the flags will be picked up by the program. The program knows what the flags are. I haven't done anything for the flags, but I just want to show you that my command argument handling works. So let's use this. As you see, it starts by saying, well, let me exit. Let's do it again. I'm going to run this, but this time I'm going to say, instead of printing on the output, prints in a results.txt. You see this greater than sign that I write here is going to redirect the output from console to a file called result.txt, but it only redirects the standard output. It doesn't redirect stderr. In other words, whatever messages we have written using fprintf and stderr, like those fatal error messages, they will still appear on the screen because they will not be redirected. But anything else, all the results that, for example, integer cell :1 or double cell :4.2 or string cell hello, those will not appear on the screen because I have redirected the result, the output to result.txt. That's a very common practice. They will do it, and this is very common. So make sure to understand it. Greater than followed by the name of a file. Now, does this greater than consider to be part of the command line arguments? Can I read that using like argv and argc? The answer is no. That's not going to be part of your command line arguments. So don't worry about that. This is only redirecting the output without affecting your command line arguments. So let's do that. Again, as you see, I still see this note because I haven't printed it using normal printf. I used fprintf, remember? Let's give some input. I'm going to use the same input that I have given before, which is 1, 4.2, 2, 0.4, 2 point, hello, right? And as you see nothing on the output. Why don't you see anything? Why don't you see those outputs on the console? Because I have redirected to this file. So let me add a few more things. Let's say I'm going to add an extra hello world, 1.00001 or 3. And then I'm going to press Control D. Control D basically end the program. And now it's time to list all the files. And as you see, I have a result.txt added to my folder that's just got created after I redirected my output to result.txt. Now, if I open this, if I say cat result.txt, I will see the outcome of the first row, which was these. It tells you which one of them are double, which one of them are a string, which one of them are integers. And then the output of the second row, which is the hello world and this number. And that's pretty much it. Why don't I see this 0.3 here? Because by default, the double gets has only 6 digits of precision. So if you need more than that, you need to use the precision option. You need to use 0.7f or 0.10f, something like that. So I think you can basically start working on this. I'm going to post the starter code and then the auto grader. And as I said, the empty cells are going to consider to be part of the extra credit, 15% extra credit.